The broadcast is now starting. All attendees are in listen-only mode.
Hey, welcome everybody to Coffee with Caleffi. Thanks for tuning in today. I hope everybody's having an enjoyable summer. I doubt that there's many of us in the industry that haven't benefited from John Siegenthaler's knowledge and teachings over the years, and we're delighted to have him here with us today to do this presentation. I consider him a friend and a guru in the industry. So when I say the industry, I mean, we talk a lot about hydronics, but the topic today that we're covering is mainly a plumbing topic. So, the topics that we cover would include geo, solar, hydronics, and plumbing. So we're on a plumbing specific topic today. So all of our hydronics. So today, issue number 21 is just hitting the street. It just came off the printer last week, so that should be in the mail within the next couple days to a week. So keep an eye on that, and that's the one that Siggy's going to be talking about today. So, yep, I think it's all yours, Siggy. Thanks for coming.
Well, thank you, Hydrod, and thanks for tuning in this afternoon, folks. As Hydrod was mentioning, Hydronics 21 going out this week. The topic is recirculating domestic water systems. Today's webinar is going to parallel that, kind of summarize it. We're going to be taking a look at simple systems, what we call single loop recirculating systems. This would be typically used in a house or perhaps a small commercial building. We're going to branch out into larger systems there where balancing becomes an issue, and we'll talk about some brand new hardware coming from Caleffi that is specifically designed to help balance out a recirculating domestic water system. And of course, we've talked about balancing in the context of hydronic heating and cooling systems in past webinars. There's a difference between the criteria and the methodology of balancing a domestic hot water recirculation system compared to a hydronic heating system. There are similarities, but again, distinct differences, and we'll talk about that. And we're going to look at a new product coming from Caleffi called the ThermoSettere valve, specifically designed for balancing a multi-branch domestic hot water system. So let's start off with a very simple, basic domestic hot water delivery system. This would be perhaps typical in a house or a small commercial building. We're assuming over here on the left that we've got a tank type water heater, and we have a domestic hot water trunk pipe that comes out from that. And that trunk pipe will go along the building, may go through the basement. It may change pipe sizes depending on how large the system is. But the basic idea is very simple. Each fixture simply taps into that trunk line to draw hot water. And then, of course, we have a cold water line that supplies water back to the water heater as well as cold water out to the fixture. Now, this would be called a standard trunk and riser system. One of the potential issues with a system like this, especially one that is stretched out over a long distance within a building, is when there is a demand for hot water at those fixtures at the far end of the distribution system, especially when that demand occurs after a period of non-use. Let's say it's the first thing in the morning. Let's say the master bathroom shower is at the far end of the distribution system. You open the faucet and you might wait 30 seconds or more for hot water to actually make its way from the heat source to that fixture. And of course, that's annoying. And most people today are used to instant response in a lot of situations. So waiting 30 seconds for hot water to reach the fixture is a bit of an annoyance. And it also wastes water. If you consider that when that fixture was last used and hot water was drawn through it, there was hot water present in that entire trunk piping. And over a period of minutes or certainly hours, and depending on whether or not that pipe is insulated and also what kind of ambient air temperature surrounds that pipe, that water could completely cool down to ambient temperature. And there was a study done that estimated that an average house wastes over 3,600 gallons of heated water per year, simply forcing that water through the fixture and down the drain while waiting for hot water to get to the fixtures. And certainly that wastes energy, but it also wastes water, and especially out west where water is a very precious commodity these days. The energy waste is probably considered secondary to the actual cost associated with wasting the water. The other aspect of a standard trunk and riser system is that there's no protection against scalding. If the thermostat on that water heater is turned up or malfunctions, potentially scalding hot water can go down that system and go right to the faucet and go right on somebody's hands or through a shower. And that certainly is something we want to avoid. So as we develop this system farther, we're going to incorporate recirculation to take care of that long wait time, or eliminate that long wait time at those far fixtures. But we're also going to incorporate devices for safety. So let's take it to the next step. We're adding a recirculation circulator here. This would typically be a very small, low power stainless steel or bronze circulator. And if we actually look at the piping itself, we'll see out here at the farthest fixture, instead of the trunk just ending at that fixture, it continues into a smaller pipe size, and this pipe comes all the way back, and we'll call that the return pipe. It goes through that circulator. It is important that there's a check valve downstream of that circulator, and the reason for that is we don't want cold water that's coming in and either going out this way or back towards the water heater. We don't want that cold water backing up through this pump and potentially going to the hot water risers on the system if the recirc pump happens to be off. So in many of these diagrams, you'll see in the case of a single loop system, a single check valve. In a multi-branch system, you'll see a check valve on the return of each one of those branches. Now, the recirculation pumps may run 24/7. I think traditionally that's the way they've been set up. But today there are more advanced techniques on that. There are pumps that have timers on them, so they can be set to run at pretty much any time hot water is expected to be immediately available at the fixtures. They might be turned off, for example, at night, maybe at 11 p.m. they're turned off, and at 6 a.m. they're turned back on. And then even more recent than that are pumps that have the intelligence to learn the hot water demand patterns of a building over several days and then adapt to that. So they have the intelligence to turn themselves on and off based on historical demand for domestic hot water. Again, these are very small circulators. Here's a couple of examples of typical recirculation pumps. These may be in the range of perhaps 10 to perhaps 30 watts in a residential application, but in larger commercial systems, they could be much larger than this. So single loop systems in smaller buildings, typically small pumping requirements. And you can see these two pumps happen to have manually set timers on them. And again, no scald protection is present. We've added recirculation, but we still got to deal with that scald protection. So let's do that. We'll take it to this diagram. We have the same piping layout here with our recirculation circulator, but we've added an ASSE 1070 listed point of use thermostatic mixing valve. These valves are designed to not allow scalding hot temperatures. I believe the highest setting is about 120 degrees Fahrenheit. If the water coming from that heat source was hotter, they will blend cold water together with that potentially scalding hot temperature to deliver nothing higher than 120 degrees or less if they're set to a lower temperature to the fixture. And you can see there's one of these on each of these lavatories on this shower head. Over here, though, we've got a shower head that actually has a built-in equivalent of that valve. It's an ASSE 1016 rated shower head. So that would have built-in thermostatic protection against scalds. When that type of fixture is present, you don't need to have a 1070 valve. So it could be a combination of fixtures that have built-in thermostatic protection and on a simple lavatory using a 1070 valve. Here's a photo of a typical 1070 listed valve. This one is installed under a lavatory. You can see the hot and the cold water comes in on the side ports. There are check valves built in, and then the mixed water temperature leaves and goes up to the fixture. Okay. Now, when we have another piping situation here, if we start at the fixtures, you'll see there's no 1070 valves. We don't have point of use temperature protection, but back here closer to the water heater, we have what is called a point of distribution thermostatic mixing valve. This is listed under a different ASSE standard. It's a 1017 standard. And depending on the type of valve that is used there, we may have to install some additional balancing in this system. When we have a 1070 listed valve that cannot completely close its porting, we have the potential for temperature creep in the loop. In other words, the temperature of the recirculating loop may get higher than what we want because of the inability of that particular ASSE 1070 valve to not close its hot port, or it may get cooler. And when we have that type of valve, we need to establish a balance between the rate of heat loss from the recirculation loop and the rate at which heat moves from the heat source into that loop. If we have that balance established, we will have stable temperatures in the recirculation loop. And to do that, I've added a couple valves into this piping schematic. Of these two, this bridge valve is the more critical. It actually controls the rate at which water from the recirculation loop moves back towards the heat source. As we open that bridge valve up, we're allowing a faster flow of water to leave the loop and go back to the heat source, and that would represent a higher rate of heat transfer between the heat source and the loop. As we close that valve down, we're going to limit that heat source. Now, if the point of distribution mixing valve can completely close its hot and cold ports, these balancing valves can be eliminated. So again, the need for these balancing valves is dependent on the ability of the 1017 valve, the point of distribution mixing valve, to fully close its ports. Okay. And there are several types of valves. Caleffi makes several types of balancing valves. This happens to be a variable orifice balancing valve that is made with a non-lead brass, no lead brass, so it conforms to the US requirements. But the thing to remember about manual balancing is it has to be done when there is no hot water draw from the fixture. So perhaps it would be at night or some other period where when these valves are being set, there is no demand from the fixtures. And Hydronics 21 does get into a more detailed explanation of how to go through that procedure. Okay. Now, here's an example of a new product Caleffi is just releasing called the Tank Mixer. This is a ASSE 1017 rated point of distribution mixing valve, but it's been combined with another fitting and this flexible hose. And basically, if we take that product, you can see it applied here in the schematic within that purple envelope. When it is ordered with press fittings, the way it's shown here, this can be completely installed without any soldering. So this makes for an easy retrofit where we have a perhaps a recirculation loop, but no point of distribution temperature protection. It is available with other types of connections, but here we're showing the press fit just to emphasize that it can be installed without any soldering, and it can be used with or without recirculation. In the schematic up here, it shows a recirculation pump coming into the side port of the of this portion of the product, but you can see that cap there. If that cap is actually left in place, it can be used without recirculation as well. Okay. And this does not require any other balancing valves. The thermostatic valve in this product can completely close its ports, so that eliminates the need for any balancing. Okay. Now, another potential way to approach temperature control and recirculation, this would be more typical in a commercial system, is using a motorized mixing valve. There are products on the market now and more to come. The basic idea is that we have a 3-port mixing valve that has a motorized actuator on it and some type of a controller. And of course, this brings the potential for intelligence beyond just a simple thermostatic element. It can allow for different temperatures at different times. It can actually measure supply temperature as well as return temperature and generate a report, record data that verifies that a specific temperature has been maintained in that recirculation loop. One of the key uses for this type of valve is it's what's called thermal disinfection. This would be where we're going to take the recirculation loop to a high temperature for a period of time. It may be a matter of 10 minutes to perhaps half an hour. It could potentially be longer than that, but the idea is we're going to an elevated temperature sufficient to kill pathogens in the water, specifically Legionella bacteria. And during that sterilization cycle, it's important that we continue to provide skull protection. So you'll see there are ASSE 1070 mixing valves shown on these fixtures. At other times, the motorized mixing valve may go to a reduced temperature, simply reduce heat loss in the recirculation loop. Okay. So again, this is kind of the this is where recirculation and mixing is going, primarily in commercial systems. So look for, again, new products coming out on that in the near future. So let's summarize. We've started with a very basic system. We've talked about adding recirculation. We've talked about adding skull protection, and we've talked about providing protection against Legionella. So again, a summary. We want to provide essentially immediately available hot water at every fixture during any time when that water is deemed necessary. Now, again, that might be 24/7, maybe in a hospital or healthcare type facility, but it could also be a specific schedule. We want to reduce the waste of water by eliminating having to clear water that was previously heated but has cooled from just standing in the pipe. We want to reduce that. We want to ensure that the water is delivered to the fixture at safe temperatures, typically less than 120 degrees. That graph that just popped up here, again, you'll see this in Hydronics 21. It shows a relationship between the water temperature and the time to a partial burn or a very serious burn. And we want to ensure that we do not create conditions such as stagnant water in dead legs of the plumbing system or insufficient temperatures in the recirculation loop that would allow Legionella bacteria to grow. So we call that a total system concept for domestic hot water distribution. So let's get into some of the specifics now on designing a single loop recirculation system. We have to know part of the design procedure is to determine what is the heat loss of the piping, because as hot water leaves the heat source and moves out through the distribution system, obviously there's heat loss from the piping, and that heat loss is going to depend on the size of the piping, and it's also going to depend on is there insulation on the piping. It will also depend on the ambient temperature around the piping. So this graph shows the rate of heat loss from bare copper tubing still being the prevalent material for hot water distribution. And the way this graph is used is we calculate the temperature difference between the average water temperature on the supply side of the system. Now, this would be the average temperature between where the water leaves the heat source and what the water temperature, the hot water temperature, would be at the farthest fixture. And we can determine what that temperature drop is. We can just set a value that we want to enforce, such as 5 degrees or perhaps 10 degrees. And the average temperature would just be basically if it was a 5-degree drop, we would take half of that drop, 2.5 degrees, and subtract that from the supply temperature. That would be what's called T water here, our average water temperature. And from that, we subtract the surrounding air temperature. So this gives us, if you will, the driving temperature difference that pushes heat out of that tube. And when we find that value on the horizontal axis, we read up to a curve for the tube size, and I'm showing sizes here between 1/2-inch copper tubing all the way up to 2-inch copper tubing. The ASHRAE handbook, one of those ASHRAE handbooks does have data for larger copper tubing in it. It also has data for steel piping, not that that piping is very infrequently used for domestic hot water. So we'd go up to the pipe size, and then we'd read over to the left, and in this case here you can see we're a little over 30 BTUs per hour per foot of tube. Now here's a graph, same procedure, the only difference being this graph assumes 1/2-inch elastomeric foam insulation on the tubing, and the numbers are substantially lower. For the same temperature difference and the same tube size, we have definitely lower numbers over here. So whether or not the tubing is insulated certainly is going to affect it. So again, we determine average water temperature in the supply pipe, or whatever the pipe is. We could actually use this same graph for a hydronic system. We just need to know what is the average water temperature in the segment of the piping we're looking at, subtract the surrounding air temperature. That's the delta T. We find that on the horizontal axis. We read up to the tube size, and then we read over to the left to get our BTUs per hour per foot. And of course, knowing the length of the piping, or at least a reasonable estimate for the length of piping, we can get an estimate for what that heat loss is. Okay, so let's go through an example here, okay? We're going to calculate the heat loss on the piping that's shown in red. Now, the American Society of Plumbing Engineers handbook on designing domestic hot water systems, they use a criteria where essentially we will pick an allowed temperature drop from the heat source to that farthest fixture, and we're going to base our recirculation system on that temperature drop. And because of that, it's only necessary to estimate the heat loss in the supply piping. Now, I do know that in some jurisdictions, specifically California, there are some regulations that do require calculating the heat loss on the return piping as well, and including that. It's a different criteria. Certainly the data that we just looked at for heat loss in copper piping could be used there. I believe some jurisdictions also require thicker insulation compared to the 1/2-inch insulation we looked at. And again, there are data sources out there for different types of insulation, different wall thicknesses. So the general concept is we need to calculate the heat loss of that piping. So let's assume that the red piping is 1-inch bare copper tubing. It's going to have water at an average temperature of 120 degrees Fahrenheit, and it's going to cover a distance of 50 feet, and it's moving through a space, a relatively cool space, 55-degree Fahrenheit ambient temperature. So let's calculate what that loss is. Well, the solution is straightforward. Our average water temperature is 120. Our surrounding air temperature is 55, so the difference is 65. We would find 65 on a graph, go up to the curve for 1-inch tubing, and then read over here. And if my eyesight is helping me here, we're at about 33 BTUs per hour per foot of tubing. So again, an estimate is 33 BTUs per hour per foot, 50 feet of tubing, roughly 1,650 BTUs per hour. There are more accurate methods for calculating heat loss that would actually track the temperature drop along the pipe. Theoretically, would be an exponential drop in temperature. You could do that. It's really marginal in terms of what additional accuracy it does bring. So keep in mind, these calculations we're looking at are a compromise between hyperpure but more complex theoretical calculations and calculations that are fairly easy to do. Now, once we know our heat loss and we know the allowable temperature drop between the heat source and the farthest fixture, we can calculate a necessary recirculation flow rate. And I'm sure some of you recognize that equation. We use that equation quite a bit in hydronics. It's essentially an equation for water, and it relates a flow rate, a temperature change, and a corresponding rate of heat transfer. If we know any two of these three parameters over here, the flow, the rate of heat transfer, or the temperature change, we can calculate the other one. All right, so let's assume we've got domestic hot water piping. From the heat source to the farthest fixture is 100 feet of 1-inch bare tubing. Water enters the pipe at 135 degrees, and we're going to allow a 5-degree drop between the heat source and that farthest fixture. So half of that would be 2.5 degrees. If we subtract that from 135, we'd have 132.5 as our average water temperature in the supply pipe. We're going to assume that the surrounding air temperature in this example is 70 degrees Fahrenheit. So let's go ahead and calculate our flow rate. Well, we're going to start with a calculation of the heat loss. So again, based on those graphs that we just looked at, here's our average temperature, 132.5. Subtracting our air temperature, we have 62.5. We go back to that figure, and for 1-inch tubing, it worked out to about 32 BTUs per hour per foot. We have 100 feet of pipe in our supply run, so it's about 3,200 BTUs per hour. Now again, I want to emphasize, this is just the supply pipe out to the point of the farthest fixture. Next step, since we know the rate of heat loss and we know we're allowing a 5-degree temperature drop, we put those two into our formula, and that formula will calculate roughly 1.3 gallons per minute of flow, which of course is a low flow rate. That would easily be handled by a 1/2-inch copper tubing. And that's typically the case. The recirculation flow rate, sometimes people get confused on this. They assume it has something to do with what the water demand at the fixtures is, and it really doesn't. It's really just a flow rate that is adequate to make up for the heat loss of that supply piping. And especially if that piping is insulated, that would certainly drive down the heat loss, and that will drive down the required recirculation flow rate. Okay, now we've got the flow rate. Before we can select a circulator, we need to know what the head loss of that recirculation loop is. So we get back to some kind of classic hydronic type calculations. We're going to use this equation here. This is actually, for the engineers out there, this is a simplified version of the Darcy-Weisbach equation, which is in fluid mechanics the classic equation for calculating head loss in a piping system. And it specifically applies to smooth tubing. So copper, PEX tubing, PVC tubing would apply here, but this would not apply to, for example, steel piping, because it has a higher internal roughness factor associated with it. So essentially, there's a few things we have to pull off a chart or off a table. I'll run you through this. The A factor here, this is a factor that quantifies the physical properties of the fluid in the circuit, and of course in this case it's water. And the physical properties that we're looking at that are in a sense built into this value are density and viscosity, and both of those are functions of temperature. So we go to this graph at whatever the average water temperature is in that supply pipe. We'd find that number on the horizontal axis, read up to the curve and over to the left. Simple procedure to get the value of A. The next one here, C, says a factor determined by the type and size of tubing. Well, I've given you a table over here on the left where we could calculate these, or simply look up the C value for different sizes of copper tubing as well as some sizes of PEX tubing. This has to do with the cross-sectional area and the diameter of the tube. And then the last factor in parentheses here, L, is just the length of that piping segment. And then finally, once we get those three numbers, we multiply by the flow rate in gallons per minute, and that flow rate needs to be raised to the 1.75 power. And that's how we determine the head loss of that loop. So again, let's go through an example. Now we have to look at both supply side and return side. So let's assume we've got 100 feet of 1-inch tubing, bare copper tubing on the supply side, and then we also have 100 feet of 1/2-inch copper tubing on the return. Using the formula, we can look up the head loss or calculate the head loss of the 1-inch tubing, and it actually works out very low. It's a little bit over roughly 1/8 of a foot of head. That's a very, very low head loss. Now that's going to go up when we go to the 1/2-inch tubing, because of course the 1/2-inch tubing is much more restrictive. So there's a calculation for the 1-inch supply side. And here's the calculation for the return piping. And really the difference here, same flow rate, same A value because it's the same fluid essentially. The difference is in that C value for 1-inch tubing versus 1/2-inch tubing. And you could see significantly more head loss due to the 1/2-inch tubing. Still relatively small value. Now, just to be conservative here, we're going to of course add these two together, and then I'm going to apply a 1.1 multiplier. That's to add 10% to account for fittings. It's strictly an estimate. If you want to be more accurate, you could go through and do an estimated count of how many elbows and perhaps if there's some ball valves in the system. Whatever the fittings are, you can look up the equivalent length of those fittings based on their size, and you could include that equivalent length in the lengths up here within these calculations. Oftentimes before these systems are constructed, there's simply no way of knowing exactly how many fittings are in there. So it's not uncommon to take an estimate based on perhaps 10% accounting for these additional fittings. And still, even with that 10% added, we're under 3 feet of head. So a flow rate of roughly 1.3 GPM and a head loss under 3 feet, you can see why these recirculation pumps, at least in these relatively small single loop systems, are pretty small. Okay. Now, let's move on. Let's talk about recirculation in much larger systems. This year, the AHR show was out in Las Vegas, and I remember checking into a hotel out there, and the check-in clerk was proudly mentioning that there are 5,000 rooms in this particular hotel, but it wasn't the biggest hotel in terms of rooms. There was one hotel in Las Vegas that had 8,000 rooms. Now, I'm sure that's not all a single domestic hot water supply system, but even if it was 5 individual systems, imagine supplying 1,000 fixture groups with a recirculation system. We're going to have much larger pumps, and we're going to have a different type of piping layout. It's not going to be a single loop that goes around through the entire building trying to connect to 1,000 different risers. Here's a typical riser system, a multi-branch system. Start at the heat source over here. We have the trunk, and we come out and we hit the first riser. Now this, for example, in a high-rise building, we may have a riser that goes up through, and you can see the idea is that we have a group of fixtures, typically a lavatory and maybe a shower fixture that taps into that riser system. And up at the far end of that first riser, we have a U-turn, and then this would be our insulated return piping. And down here, we're going to zoom in on a detail right here. We have in this particular system, a manually set balancing valve, like we talked about before. And here's actually a photo of a manually adjusted balancing valve. And remember, we talked about that check valve. That's very important that we have a check valve at the end of each of these recirc branches. The reason for that is depending on how the domestic hot water is drawn from the fixtures, different fixture groups at different times can create pressure differentials in the system beyond the pressure differentials of any kind of a recirculation pump. And those pressure differentials can actually cause cold water to go back up through those return pipes. And we don't want that. So we want to make sure we've got a check valve at the return end of each of these recirc riser systems. Now, this I'd liken this to kind of a standard vanilla approach to balancing. It's been the approach that's been used for years, but there is some baggage associated with this. One is that we're going to have a device to adjust a manual balancing valve. Now, this particular valve that we're looking at is a variable orifice manually adjusted balancing valve. It does not directly read flow rate. When you turn the knob of the valve, if you want to know what the flow rate is, it has to be connected to a manometer. And this, you can see a couple hoses here that are tapped into the valve. And in the background here is a mechanical manometer that's going to read a differential pressure across the valve. And these valves are manufactured so that there is a precise relationship between flow rate and differential pressure. And essentially the manometer gives you the differential pressure. You then take that number, you go to a chart or a slide rule, or perhaps a piece of maybe an app on your phone, and put that in, and it'll tell you what the flow rate is. Some some digital manometers allow direct reading of flow rate if the manometer is adjusted to the specific valve that is being balanced. So that's one bit of baggage that has to be dealt with. And another one is that when we have several of these in a system, when you change the setting of one valve, the other flow rates in the other branches will change to some degree. It may be a small change or it may be significant, but each time we make an adjustment, in a sense, the whole system kind of reconfigures to that adjustment. So it may be necessary to repeatedly go back to each of these valves 2 or 3 times and just iteratively dial in the flow rates until we get a set of flows that are very close to what we want as target flow rates. And again, calculating those flow rates in each of those branches is a matter of estimating what the heat loss is, estimating what the, or I should say, fixing what the temperature drop allowance is, and then making a calculation for what the flow rate in that branch should be. So in summary, balancing valves, manually set balancing valves are a possibility. Caleffi does offer 2 or 3 different types of valves that could be used there in the lead brass, but I would say they're not the ultimate solution, okay? Now, I talked earlier about the differences as well as some similarities between this type of a domestic hot water recirculation system and a multi-branch hydronic system, all right? The balancing objectives between domestic water recirc and hydronic heating or hydronic cooling are different. In a hydronic system, what we're looking for as a result of balancing is a stable flow rate that produces adequate heat transfer in all branches under design load conditions. We're going to make the assumption that all of our loads are on. We know what the loads are in terms of BTU per hour, and we're going to calculate a set of flow rate numbers that we want through each branch, and that's our criteria. That's what we're going to try to balance to. That is not what we have in a domestic hot water system, though, okay? One of the things we want to do is we want to provide a minimum hot water temperature to the farthest fixtures in all branches. And again, that's up to the designer. A typical range of temperature drop would be anywhere from about 5 degrees to 10 degrees. That would be between the heat source and the water in the pipe at the farthest fixture in each branch. And we also want to prevent stagnant water within any part of the system that has no demand. Imagine a multi-branch system, and perhaps there's a wing of the building that's only used for certain occasions, and it could go days, even weeks, without any draw of hot water. And under those conditions, pathogens like Legionella bacteria can grow. So ideally, we want a system that has the intelligence to know when there could be stagnant water and simply create conditions that prevent that from occurring. That's not something we have to be concerned about with hydronic system balancing, okay? So in a multi-branch domestic hot water recirculation system, there are going to be times when just the water demand from the fixtures makes the water in the pipe, prevents it from being stagnant, okay? Under those conditions, there's really no need for recirculation if the branch is completely filled with hot water, because many of those fixtures have been on, and a common scenario would be morning in a hotel. Most people are going to be running hot water through the lavatory or shower. So there's going to be a fairly large demand, and that may clear all the water in that riser essentially giving you hot water at the farthest fixture, even without a recirculation pump running. Under those conditions, ideally, we could close the recirculation flow in that branch and not create any adverse situation. And by doing that, we could reduce the potential pumping power. Again, think in a large system where we might even have multi-horsepower pumps running on the recirculation system. Anything we can do to reduce flow rate in that system and not create conditions that are harmful is a plus. We could use a variable speed pump and we could reduce the speed of that pump, okay? And at other times, as I mentioned, we could have hours or even days when there's no domestic water flow. And ideally, we'd like to have a system that can avoid that kind of a condition, okay? So the variability of the domestic hot water delivery system and how it's operated and the need to protect against this biological growth requires a different criteria that's for optimum balancing of that recirc system. And the criteria is based on, again, maintaining a minimum hot water temperature at the farthest fixture rather than maintaining a specific flow rate through each branch. Now, that's a pretty simple sentence, but read that and think about it carefully. It is definitely different from what we're doing in a hydronic system. In a hydronic heating system, it's all about the flow rate. In a domestic water system, it's about maintaining that adequate temperature at that farthest fixture, and our calculations are going to be based on that. In a multi-branch system, it's essentially going to be a procedure similar to a single loop system, but obviously a little bit more involved because there's more piping. So if the minimum temperature at the farthest fixture is being maintained because of draw of domestic hot water at that fixture, there's no need for recirculation flow in that portion of the system. That's not to say that other branches don't need recirculation flow. Treat each branch as if it's an independent situation that may or may not need recirculation flow at any given time, okay? Our system should automatically detect which of those risers doesn't require recirculation, okay, and make sure that we maintain that adequate temperature at the farthest fixture, all right? You might say, well, we'll just run the whole system 24/7. You could do that, and I'm sure there are systems out there, many systems out there that do that, but that is wasting energy. It's wasting electrical energy to maintain the circulation. Anytime we have circulation through a piping system, we have head loss, and head loss is electrical energy going into a circulator. So by minimizing our flow requirements and still providing the necessary temperatures, we are able to reduce our pumping power requirement. So again, you might say in a small system, it doesn't make much difference, and arguably so, perhaps in a single family residence, but in a large commercial system, this could be a major savings. And it certainly represents a state-of-the-art approach, variable speed circulators being used in recirculation domestic systems. Now, to do that, Caleffi's developed a new valve, and it's called a ThermoSetter. It is designed to be installed on the return piping in a recirculation system. I'm showing it here near where the recirc pipe joins into the recirculation trunk. This would take it back to the heat source. Actually, it could be anywhere along this recirculation pipe. This is the last fixture served by the branch. So actually all this piping is recirc. There's no other tappings into that pipe. Obviously, it has to be in a location on that recirc line so it's accessible, okay? And the way to describe this valve is it opens as necessary to ensure that that minimum temperature at the farthest fixture is being maintained. When that temperature is being maintained by normal hot water draw, this valve is going to throttle down to a very low CV value. It's going to allow just, if you will, a trickle of hot water to go through it, just enough so that the temperature sensing element can continue to monitor that temperature. If the temperature starts to drop off due to non-use of the fixtures, this valve is going to start to open itself up and allow more flow to go through. So it's a temperature responsive valve based on what's going on with the actual domestic hot water draw in that particular riser at any given time. The minimum CV on this is 0.23. Now, many of you know what CV is. It's actually the flow rate in gallons per minute that creates a 1 psi pressure drop across the device, in this case the valve. So a CV of 0.23 is very low. It essentially just allows that trickle of flow through the thermal element of the valve to make sure that that valve can respond when it needs to. Okay. Thermal balancing ensures adequate flow in each branch and reduces pumping power requirement. So let's take a look inside the valve. What's going on? Well, it's a no-lead brass body valve, and here is the thermostatic actuator. Now, this is very similar to the actuators that are used in the 1070 valves, the 1017 valves. Sometimes valves with this type of actuator are used in hydronic systems. It's a specially formulated wax that expands and contracts against a spring. And the knob on the valve, as you can see up here, you would set the temperature at which this valve basically closes itself off. This particular valve is shown with a mechanical thermometer, so you can actually read the water temperature at that point on the recirculation system. That can be pulled out of the well, and it can be replaced with a temperature sensor if you're using some type of electronic control system. Let's look at what the valve does, its response. Let's assume that we've set this valve for 140 degrees. All right, so at 140 or above, this valve is throttled down to a minimum CV of 0.23. It's basically in its monitoring mode. A trickle of water is going through it, and it's monitoring the temperature. Now, let's assume that the temperature starts to drop off because of lack of use of hot water in that particular riser. You can see as the temperature drops below 140, the CV value progresses upwards, and it actually goes up to a maximum of 2.1 when we have dropped, let's see, from 140 down to 80. So a 60-degree proportional range on that. Again, lack of hot water demand in the riser allows the valve to open, and depending on the water temperature going through that valve, if that water temperature comes back up because there starts to be a demand from some of the fixtures, then the valve will start to throttle down the flow. If the temperature continues to drop or simply holds, the valve is going to go to a CV as necessary to keep that flow where it needs to be. Now, here's the same valve body, but it has a different trim configuration. And just to show you the difference, let me go back up to this slide. I'm sure some of you noticed this empty chamber right here in the valve and wondered what that's about. Here's what it's about. Some systems that will use this type of valve are also going to have temperature sterilization, thermal sterilization. Basic concept, our heat source is going to go up to a high temperature for a period of time, high enough that it can kill Legionella bacteria. And we want this valve to be able to recognize that, because we don't want to restrict flow through a riser when we're in a thermal sterilization mode. We want that flow to increase. So this second thermostatic element is strictly responsive to a thermal sterilization cycle, and this graph will show what's going on. The red portion of this graph is what we just looked at. We've got a valve, we're assuming it's set for 140, but let's assume that that water temperature goes up because our system has gone into a thermal disinfection mode. When that temperature gets up to roughly about 155 degrees, this valve is built with the assumption that that represents a thermal sterilization cycle. The water temperature has reached 155 degrees. So what happens is this second element starts to open up a flow passage through the valve as a whole, and you can see the CV value goes back up. It actually goes up to about a 1.2 during thermal disinfection. We're allowing a higher flow rate of this hot water to go through to make sure that we're getting adequate flow of that hot water to all portions of the system. And once we get up over about 170, it starts to throttle back down again. Okay, so we have that built-in response to a thermal disinfection mode. And there's another configuration, same valve body. It still has the primary thermostatic element up here, but now the second thermostatic element has been replaced by an electric actuator. And if you look at that actuator, I'm sure many of you will recognize it's the same type of thermal actuator that is used on, for example, a radiant panel manifold system. It's a low voltage actuator. Again, it uses a formulated wax compound and a small electric heating element. When we apply 24 volts to that actuator, it's going to retract its stem and it's going to allow flow to go through that valve. So now we have control over when this valve goes from a restrictive flow, where the CV is very low. We can control when we want a higher flow rate through that valve. So, for example, we may want to do a chemical disinfection cycle rather than a thermal cycle. If that's the case, we want to have a higher flow for a certain period of time so we get proper distribution of the sterilization chemical through the system. Basically, it's just a matter of controlling when there's 24 volts applied to that actuator. 24 volts, roughly about a 2-minute cycle time. That valve will be in a bypass mode for sterilization. Remove the 24 volts. A couple minutes later, that sterilization portion of the valve will close. So what it looks like on the graph, again, the red portion is still the same, but I'm assuming here that the disinfection cycle will start at about, at about 145 degrees. So you see we have just a step change in the CV value. We go from our minimum CV of 0.23 right up to the 1.2 that would hold during the entire disinfection cycle. When we have a multi-branch system, we could actuate different valves at different times. We may want to do a thermal disinfection in just one portion. I'm sorry, a chemical disinfection. It could be chemical or temperature-based, but a disinfection mode in just one portion of the system at a given time and not other portions. We can control that simply by when we apply power to this actuator. So in summary, we have a common valve body that can be trimmed out 3 different ways, 2 of which are based on sterilization cycles. So let's go through some calculations again. A little more involved, but I think you'll see similarities here between the single loop calculations and these multi-branch calculations. So I put together a multi-branch recirculating system. In this case, it has 3 risers. The green text here describes the pipe size and the length. So we'll assume that first supply riser is 100 feet of 1-inch tubing. This first segment over here on the trunk is 100 feet of 1.25 inches. And you'll see some other pipe sizes and lengths in here. There is one mislabeling. We are assuming 140 degree water leaving the source, and of course it says 140 up here. This should be 130. Okay, where our criteria is going to be 130 at the farthest fixture in each of these branches. So we're allowing a 10-degree drop in our piping. So the dark, heavy green lines here show the supply piping segments that we need to analyze. Okay, and again, we have a length and we have a pipe size specified. We have a criteria where we have the temperature here being 10 degrees lower. Again, we want 130 here, 130 here, and 130 here. And we have 140 leaving the heat source. So we know what the temperature drop is. We're going to be able to estimate what the heat loss of that piping segment is. It is insulated copper. We'll assume 1/2-inch elastomeric foam insulation. So we can calculate a flow rate in each one of these branches and then add them up for a total system flow rate. So again, we're going to make reference to our chart, in this case, the chart that had the 1/2-inch foam rubber insulation. And I just summarized it here. For the 3/4-inch piping, it's a heat loss of 9.5 BTUs per hour per foot. And as you'd expect, it goes up to higher value there for 1-inch piping and still higher value for 1.25 inches. All these were calculated based on an average water temperature of 135. Again, averaging between the source at 140 and the far point of the distribution system or each branch at 130. So we can calculate what I've done here. I've just added up the total lengths of each pipe size multiplied by the rate of heat loss per foot, and then total it all up. So we're just under 7,500 BTUs per hour for our total heat loss. So we can start with what our total system flow rate, recirculation flow rate is. We take the total heat loss, 7,450 BTUs per hour, and we're going to allow that 10-degree drop from 140 at the heat source to 130 at the farthest fixture in each branch, and we come up with roughly 1.5 gallons per minute. Again, I want to emphasize this is only the heat loss of the supply piping, and it is based on the criteria of allowing a 10-degree drop from source to the farthest point. It is not including the heat loss of the return piping. So let's put a diagram down where we just kind of clear away the piping and just look at these green segments. We've got 130 degrees listed here at the far end. We know our total flow rate here is 1.5 gallons per minute, but we don't yet know the flow rate in each branch. So I've called those flow rates F1, F2, and F3. We do know that the sum of those three has got to equal 1.5, and that's one of the equations that we're going to solve to come up with these other flow rates. And the other thing is, based on the pipe size and the pipe length, and the fact that it's average water temperature of 135, and it's copper tubing with half-inch foam insulation, we know what the estimated heat loss is. So again, we know heat loss and we know temperature drop, allowing us to calculate flow rates. So we'll put down a few equations here. We know the total of all three flow rates is 1.5. Now, we don't know the temperature at that point in the system right there. I'll call that temperature T1. That's the location where that first branch takes off from the hot water trunk, all right? But we do know the heat loss in this segment, and we know the flow rate, all right? That heat loss is 1,290 BTUs per hour. And we know that we've got a flow rate of 1.5. So this portion of the equation represents the temperature drop from that point to this point, from 140 at the source to this temperature node T1. So if we start with 140 and we subtract the temperature drop, we get about 138 degrees at this location in the system. Okay, so again, that's a straightforward calculation where we know 2 out of the 3 parameters. We can calculate the third, and in this case, we can solve for what that temperature is right there. Now, based on the heat loss in this piping segment, we know there's a 10 degree, we know the drop is from 138.28, what we just calculated here, down to 130. So there's our delta T right there. And we know the heat loss rate for that segment estimated at 1,120. There it is. So the flow rate in that first branch, we can calculate 0.27 roughly. Okay. We were kind of joking a little earlier. This has probably got too many significant figures in it. We don't really know that flow rate down to 1/1000th of a gallon per minute. It's simply a calculation. We're going to maintain a little bit higher accuracy and then add it together and then round it off. So we continue to do this kind of an analysis. If we know the flow rate going up here and we know the total flow rate, we could subtract this branch from the total and get the total of F2 plus F3. That's what we did here. And then the next thing is we're going to estimate the temperature here, and we know the heat loss here, 1290. We know the total flow rate is F2 plus F3. All right, so we can write that as an equation, and we can write another equation down. We can actually solve now for T2 because we know that if we take 1.5 and subtract that, we have 1.23 gallons per minute. We actually plug that in there. And so we know that temperature as 136.18. And we just kind of keep repeating these types of calculations. And in the end, we solve for all 3 flow rates. They all have to add up to 1.5 gallons per minute. Again, I maintain a little bit more significant figures than I really should, but I just wanted to maintain those, so we add up to 1.5. Now you can see that the highest branch flow rate, actually it's mislabeled here, it should be branch flow rate 3 out here. This is going to be the highest flow rate because it's the longest path for one, so it's going to have the greatest total heat loss, right? So now what I've done is drawn in the recirculation lines in blue and just label the flow rates that we have, just kind of putting down the results on the diagram. Next step is we have to calculate head loss. Now that we know the branch flow rates, we have to go through and calculate head loss. And this is where things can get complex, if you want to make it complex. When we have this kind of a piping system, we call this a parallel piping topology. It means that we have parallel branches, and it's sort of like having parallel electrical resistors in a circuit. There are very formal methods to analyze this kind of a system. They can get quite complex. The typical conservative way to analyze this is to identify the path, and that would be, again, from, if you will, from the discharge of the recirculation circulator back to the inlet. What is the path of greatest resistance in this system? We have 3 potential paths from that circulator. We could go up through here, back on that recirc pipe. We could go out through here and back, and we could go all the way out and up through here. Now, you might be looking at that and saying, well, it's obvious that it's that farthest path because of the length. Keep in mind that every situation is different. The larger or the longer length might, in some systems, have larger pipe sizes. That's going to reduce the head. There may be other flow restrictions in some of the shorter piping branches, maybe more fittings, for example. So we can't always generalize and say that it is the farthest branch. In this case, though, it is, because it has the highest flow rate and it also has the greatest length of piping. So it's a given that that is the branch we're going to analyze. When you're not sure, the best thing to do is to actually calculate the head loss in each branch path and simply pick the one with the highest value. I say it's a conservative assumption because what we're going to do is we're going to pair up the total recirculation flow rate with the highest head loss path. That would be adequate to get our flow through that highest resistance path, and certainly that actually leaves excess head in the other 2 lower resistance paths, but the ThermoSettere valve will throttle to take care of that. Okay, so we're going to make some more calculations. In this case, I've gone back to our table here for the C values on the different pipe sizes, just written them down, okay? And I've actually processed, let me just turn them all on here. We've used the equation we talked about earlier for smooth tubing to calculate the head loss in each segment. Now, let me just kind of trace those segments out. We're going to assume that the heat source itself, let's say it's a tank, negligible head loss. A tank is a very large cross section relative to the piping. It has, extremely small head loss. We're not even going to consider it, but we got to consider the head loss of that segment and then this segment. Now, keep in mind, these are at 2 different flow rates. This has the total flow. This has F2 plus F3. And then finally, we have to look at this segment here, which has just F3 flow rate. And then finally, we also have to look at all this return. And again, we have different flow rates at different portions of the return path because we have the other branches hooking in. So in summary, we have 6 different piping segments where we have to calculate a head loss. And there's the calculations. And then finally, we're going to add those up, okay? And we're also, we should calculate the head loss for the ThermoSettere valve. Now, we're going to assume we have a ThermoSettere valve in each one of these, but again, our path of highest resistance is this path that is the longest length. So let's assume we've got a ThermoSettere valve right here. The CV that we want to use for that valve for this calculation is 0.52. And again, that's explained in Hydronics 21. And here's the classic equation that relates head loss, flow rate in gallons per minute, and the CV value. So we plug our numbers. That's our flow rate through the ThermoSettere out there in this farthest path. Here's our CV value. So we get significant head loss there, 7.26 feet. I say it's significant in comparison to some of these piping segments, but it is part of that path, so it does have to be included. All right. So what I've done is I've actually added those head losses together, the head losses of the piping segments. I added 10% to it. In fact, yeah, here's a calculation. So here's the 6 head losses that we had for the piping segments. We sum them up. I multiplied by 1.1 to add that 10% allowance for fittings. So we have 10.25 feet. And then we're going to add the 7.26 feet for the ThermoSettere valve. So our total is effectively 17.5 feet of head loss at a flow rate of 1.5 gallons per minute. And just like selecting a circulator and a hydronic system, we would go to some pump curves now for candidate circulators. I plotted it out here, 17.5 feet of head loss at 1.5 GPM flow. And I drew a curve in. Now you can see that curve is just a little bit higher than that duty point that we've calculated, which is fine. We're going to have a little bit extra head there. It's really not going to move the flow rate much at all, but obviously we want to make sure that our circulator can produce at least 1.5 GPM against a head loss of 17.5 feet. And at that point, we can just select the circulator. Now, a summary of the concept here. This shows multiple ThermoSetters, one in each branch. And again, these are available in different pipe sizes, depending on what that recirculation pipe size is. And we're gonna combine those with a variable speed circulator. Okay. And the idea, this is very similar to modulating flow control valves in a multi-branch hydronic system, where as these various valves open and close, or just modulate in between open and close, the pump will sense that change. It'll sense it as an attempt to change differential pressure. And then based on how that circulator has been set, either for constant differential pressure or, in this case, proportional differential pressure control, that pump is going to modulate its speed in response to that change. So the idea is we're always reducing wattage going into the pump as the ThermoSettere valves throttle down the flow rate in these branches. And this graph shows the idea. If we had the pump at full speed, represented by this curve, all right, and let's say that all the ThermoSetters were in their maximum open position, where they're up there at about a 2.1 CV, we could look at the entire recirculation system as having a system curve, and we'd have a certain flow rate. Well, as those ThermoSettere valves start to reduce the flow rate, our variable speed pump will sense, again, an attempt to change differential pressure. It will reduce its speed, which brings its pump curve down. And anytime our pump curve comes down and moves to the left, we have a reduction in input wattage. Okay, so again, very similar concept to a multi-branch hydronic system. All right, and I'm going to finish up with just a couple other ideas on recirculation. This is another concept. This would apply to a single loop system where we're sensing the temperature at the far end of the supply pipe, and that sensor is feeding back to a variable speed recirculation circulator. There are circulators on the market that can do this. They have a built-in temperature controller. For larger circulators, it could be something as simple as a temperature controller with either a 0 to 10 volt output or maybe a 4 to 20 milliamp output, and that would feed a variable speed drive that would then control the speed of the pump. It's a simple idea. We're simply monitoring that temperature at the farthest fixture, and as it goes up and down, we're modulating the speed of the recirculation pump. Again, the goal to minimize our input wattage. And then the last concept, this is kind of musings of how would we potentially integrate a recirculation loop with a renewable energy heat source, like a solar thermal system, or perhaps a biomass boiler that's heating a thermal storage tank. The idea being that the thermal storage tank could have a wide variation in temperature. Let's say it's connected to a solar thermal system. We've had 3 nice sunny days. That tank could be very hot. It could be 170, 180 degrees Fahrenheit. What we're going to do is we're going to take tank water. This is not potable water now. This is system water. We're going to circulate it through a stainless steel heat exchanger with a circulator. That circulator might be on, well, it would have to be on whenever there's a potential domestic hot water draw where we want instant hot water at the fixture. So again, it might be 24/7, or it could be on a timer. But anytime that we deem it necessary to have the recirculation loop operating, this circulator would be on. It could be a relatively low power circulator, especially if this heat exchanger is located close to that tank and we have minimal head loss through the heat exchanger and the piping. But let's say we have very hot water out here, 180-degree water. The water going into the recirculation piping now, this would be domestic hot water. It could be 170, even 175 degrees. Under that condition, we want to make sure that we protect against scalding. So you see each of these subsystems here has an ASSE 1070 mixing valve set for a safe delivery temperature. So we've provided that anti-scald protection. Now each takeoff point goes to a thermostatically controlled electric tankless water heater. And I've put some labeling here. Let's assume this is a residential application. This might be a bathroom group, maybe the master bathroom group. So we'd have a shower, maybe a tub, and a lavatory. And we may have a kitchen group. Maybe we have the dishwasher, the sink, maybe some other load there. And then we have another bathroom group. We might have a laundry group. Whatever these groups are, we have lower kilowatt rated point of use tankless water heaters that are set up for each of these groups. They all draw off of that recirculation loop. Now, let's assume that we've had 3 very cloudy days and this tank is down to maybe 85 degrees. We can still heat, or I'll say preheat, domestic water. We may have water coming out of a well at 50 degrees Fahrenheit. We've got a tank at 85. We can still add some energy to that water. One of the beauties of domestic water heating with renewables is we're starting at that low water temperature. Okay, it takes just as much energy to heat that water from 50 to 60 as it does from, in theory, from 150 to 160. So we want to leverage that low temperature end of the spectrum. So we will do that with this heat exchanger, but then we're going to use the electric heating element in these water heaters to boost it to where it needs to be. If we're trying to get 120-degree water out of each one of these, remember these are thermostatically controlled electric tankless water heaters. So we can set them for different temperatures and they will modulate the power going to that element based on what that outlet temperature is. If that water comes in at 115 and the water heater is set for 120, they're only going to use the wattage necessary for a 5-degree boost. So it's a nice concept. Over at the far right is the anti-Legionella portion of the system. This would be a dedicated tankless water heater that would periodically take that recirculation loop to a high temperature to sterilize it. And that's its sole purpose. At other times it would be off. So we would have some type of control that would limit when that water heater is operating. And I did a few calculations. These can be relatively low wattage. Even a 2 kilowatt or a 3 kilowatt tankless water heater can handle it. And the reason is, remember, this is only having to overcome the heat loss of the recircle loop under thermal sterilization conditions. So if we have a specification on what this piping is and what temperature it's going to operate at, we could use our graphs that we looked at previously, calculate what that estimated heat loss is from that loop, and then make sure that our, I'll call it our anti-Legionella tankless water heater, can put out a sufficient heat to make that temperature occur. So as I say, I just want to close it out with a couple concepts that were a little different from what we talked about in the main portion of the webinar. And with that, Hot Rod, I'm going to turn it back over to you to close us out here.
Yeah, well, thanks for a great job. That's plenty of information there, and it's all the information anybody would need that's always wondered about how these systems get designed and what makes them not work properly, or pinholes in copper pipe from overpumping. All those issues are answered in these. Thanks, Siggy, for all your effort on this and for all that you do for us.
Great being with you.
and we'll see y'all in August. Bye-bye.